one thing I like about AbGradCon is the audience is pretty chill. So we're all grad students, undergrads, so I get to experiment with how I do presentations. So first I need some audience participation. Can someone give me a letter?
J.
A? J. Okay. Another letter.
C.
Okay, now a number between 1 and 1,000.
13.
I knew someone was going to say that. I'm going to go with 13. Another letter.
Q.
Q. Oh, okay, this is great. All right, now hot or cold?
Hot.
Hot. All right. Perfect. Okay. So I'm going to be talking about color. I'm going to be talking about it in a couple of contexts, all related to exoplanet habitability. We'll be talking about how we can use it to classify things now and how I'm using it in some models to classify things in the future. And I want to do it by telling the story of a planet just recently discovered, JC13Q, meaning there's many planets in this system. It's probably the most impressive planetary system ever discovered, and it has this habitable planet. It's totally real, it's there, it's got life teeming on it, but how are we going to know? Like, how do we figure out that it's there? So right now, we can't really make detections of what the composition of the atmosphere is like. We have a range, we can detect habitability out to like 0 light years. So this planet's much further than that. So what we can do now is we sort of can just make guesses. And later, people like Claire will use telescopes to actually make the detections and confirm our guesses. So as we build up these guesses, we're sort of building a library of sort of pictures of what potentially habitable planets could look like. And then we have this reference catalog. It's like sort of like an Autobahn guide. Like we're building up reference pictures, and then you go out in the wild, you actually observe something, and you try to match it as close as you can. So the first thing you sort of want to do is you want to have like ground truths to what you want to do first. You need to actually find some real planets, and what do those look like first. So we have a solar system that's pretty diverse. We do have a habitable planet, which is nice. So some of the earlier work we did was to actually look at our neighbors, stuff in our own solar system, to see what they'd look like as exoplanets. So we calculated geometric albedos for 19 different solar system objects. You have all the planets, some dwarf planets, a bunch of moons, to sort of build this picture of what our solar system looks like. And then we used that to model what they would look like around other stars. And here's our JC13Q, it's down here. So it doesn't have the spectra over it, because we want to figure out what that's going to be like. So we reaffirmed one of the things that you can do with just something as simple as looking at our own solar system, and that's distinguishing different types of surfaces. It's going to be one of the first steps when you find an exoplanet. Is it rocky? Is it gaseous? Is it icy? So even with something as simple as one of these colors, so people might not be familiar with this. R and J, these are just different filter bands. You essentially just take your spectra of the planet, you have a filter band, you just integrate over that, and it's just this broad spectra. Think of like a very low resolution spectra. And this is just a reddish color, and this is infrared, and here's a couple more infrared. So even with this very low resolution spectral data, you can distinguish different surface types. So that's something we can do using objects in our own solar system. But this can only go so far. So if you have a planet that has any sort of atmosphere, and you change the light source, that chemistry is going to be a little different. We can do things, for rocky planets like that don't have much of an atmosphere. That's not going to change much in terms of its colors. If you put it around a different star, you can adjust for how the light's going to be different. There's no chemistry really changing the atmosphere because there isn't any. So if you really want to look at something like our planet, which is around a hot star, So it's a lot hotter than our own sun, so the light that's hitting it is going to be different. So if you look at the models that we're using to simulate what those atmospheres would look like for habitable exoplanets, we find that they're sort of not good enough. They do the job of changing the chemistry of the atmosphere. You can sort of model how that light is going to change the chemistry, but they lack another key feature, which is the surface albedo spectral information. And that plays a huge role in how the climate becomes stable. So to our model, the planet kind of looks like this. It's gray. It's just, there's no color information for the surface. It's just a single value that you're using to treat the entire reflectivity of the surface. It's a single number. What we want it to look like is something like this, much more close to what it's actually like. But we do use one-dimensional models, so it's more like this, and we want it to be like this. So there's still improvement, and there's good reason to believe that this, just adding this color information for the surface is going to alter the climate of our planets a lot. So we'll do a little bit more complicated albedo diagram than what Amber showed. So we have our sun here, all the incoming energy is hitting the planet here, which is gray. We have our atmosphere. And so what all these lines are telling you is like there's, hitting the top of the atmosphere, we have all the energy from the sun. There's some being absorbed by the atmosphere and reflected off. Some is being absorbed by the surface, some is being reflected by the surface. And then here we have longer wavelengths, the infrared being emitted from the warm surface, absorbed by the atmosphere, then re-emitted by the atmosphere, or then directly radiated out into space. So if we change the starlight, that's good. We have a gray planet here, so we don't have any interaction between the albedo and the changing starlight. It's going to be pretty much the same. We can model how the atmosphere is going to change here. But if we add color to the planet, now we don't know exactly how, there's going to be changes in how much is getting absorbed by the surface, what's being reflected, and that's going to be affecting how much is then being re-radiated by the surface and then escaping into space. And this is where you're setting habitability constraints as well, because this is controlling your surface temperature, and that's going to be what you need for habitability. And I'm saying habitability, I should define that like surface water. If you have water on the surface, we'll call that habitable. So to look at this in more graphical way, we have different star spectra here. So our planet, JC13Q, is around a hotter star, so it's going to be like an F star. So it's going to be this spectra. And here we have microns, 0.5 to 2.5, so this is near infrared. And this is the relative flux for these different stars. We have the sun here in white, and then a cooler star here in red. So you can see that they're emitting, different light is going to be hitting the planet around these different stars. Here, down here, we have the reflectance. So this is that surface color, surface albedo. I have this dashed line is the flat. This is what the models use right now. It's just a gray surface. It's reflecting exactly the same in all wavelengths. And here I have an Earth model that's at the resolution of what our models sort of look at, do the radiative transfer at. So let's go for the sun. Let's start with the sun. So if the sun spectra is hitting the flat, that's okay. That's what our models had all been built to do. All these models are coming from Earth around the sun. They were used to simulate the Earth's climate. And they've been sort of ad hoc, meshed together to create exoplanet models. So you can really tell that this is something that is left over from when it was just being used for Earth, because this actually simulates fairly well the surface temperature that you get for Earth. So that's okay. If we have the sun, we can use the flat. Fine. if we change the star and it's still flat, there's really not much interaction here. Every change that's occurring is just captured by the star. But if we have a changing albedo, say this Earth model, you can see that if we change the star, we're going to be absorbing and reflecting different amounts in different parts of the spectrum now. That's going to be altering our surface temperature. So if we have a cooler star, this M star, we see that we're absorbing more, the albedo's lower over here, where more of the sunlight, the starlight's hitting. So we're going to be absorbing more there. So the planet should be hotter than if we had just used a flat. And if we're around the star that our planet's around, where a lot of the flux is at these lower wavelengths, we're reflecting a lot more. So our planet should be cooler. That makes sense. And if we're using an Earth model for our surface albedo and we use the sun, we should get the same surface temperature as we did for the flat, because that's how the flat model was chosen. So we expect, for something like this albedo, we expect cooler stars to be hotter, and hotter stars, bluer stars, to be colder. And that's exactly what we see when we change the models to accept a wavelength-dependent surface albedo. So here I have, this is temperature deviation from between the flat model and the wavelength-dependent model. This is surface temperature deviation. So you can see for M stars, these cooler stars, the surface temperatures are hotter. And for the F stars, the hotter stars, the surface temperature is cooler. This is using the Earth model, comparing it to the flat. So we have hotter, cooler. And the sun, the 0.3 albedo that you saw here, that has been around for a while, and that's been calibrated to give you the same surface temperature as what the Earth, if you had used a really accurate Earth model. So this is pretty big. This is changing how you would define sort of a habitable zone line if you're using a wavelength-dependent albedo. Instead of just using a flat line, if you had something that more represented what the surface actually looked like. So what does that mean for our planet, JC13Q? It's got so many neighbors around. I was thinking someone's going to pick a really late letter. We're just going to have a lot of planets in this system. So there's probably there's even multiple planets in the habitable zone for this. So what does this mean? We don't know what the surface is going to be for this planet. We have an idea of what a habitable surface might look like, so we could use an Earth model. But we can also look at how this line changes for different types of surfaces. Maybe there's more ocean, maybe there's less ocean, maybe there's more vegetation, maybe there's less vegetation, deserts, stuff like that. So we can sort of look at the different spectra that are around us, use those as surface albedos, and see how they would change the habitability of a planet using this new method in our model. So I'll just leave summary up here. Thank you. Thank you to my discovery team for finding this planet. So I'll take questions now.
Hey, very cool presentation, thank you. Are you planning on using your model to any actual exoplanet?
Any actual exoplanets? Yes, we are using it to model some of the recently found exoplanets.
And what did you find?
Well, we're sort of in the preliminary stages of testing it, trying out different surfaces. So the way we've been using it for current exoplanets is to use something that's similar to Earth for now, but that's still better than using a flat. So we're taking it one step at a time. Yeah.
Okay.
Yeah, we are finding that it is changing. So a 5-degree difference in surface temperature can be pretty big for habitability. So it does make a pretty big difference if you're around M stars, which are very popular to look at nowadays. So.
Hi. So I know this may be kind of a silly question, but just curious if, when you're talking about like surface albedo, are you including cloud cover in your model at all, or?
Yes, we're. So if we go back to this, if you've seen an Earth albedo, the Earth's albedo is actually very low. It would look something more like this. So this has clouds incorporated into its albedo to get it to match a surface temperature that is the same as what we find for Earth. So we use a cloud coverage of approximately what we see today. It's around like 50% cloud coverage. And if we do that, it actually gives us the same surface temperature, which was a nice check. But it is still not, it's not like a cloud layer in the model. There is work on incorporating those. It's a very difficult problem. So there isn't a super good solution yet on how to incorporate it into a 1D model, but it's being worked on.
On your slide where you were showing the different filters, it looked like you had gas, ice, and rocky. Does that mean that you are not taking into account water worlds, or are they considered part of ice?
So these are just planets in our own solar system, or objects in our own solar system, because there's moons here. There's a lot more dots than 19, because there's some multiple observations. This is like Neptune or something, like this cluster. So yeah, each one of these is one of the objects in our solar system that I had on this. But if you did have so Earth is pretty much, it's very close to a water world. And we put it in the rocky group, and it matches up, which is interesting because water in these wavelength ranges looks very close to rock. It's actually it's just very dark. It just absorbs everything. So that's a lot of what these rocks actually look like. So that's an interesting question to disentangle. If you had just these to work with, how could you distinguish between a water world and a rocky world? So, yeah.
Any other questions? Alrighty.
All right.
Thank Jack.